Let's study 10th standard ICSE physics, the numericals of chapter 8, exercise C, current electricity. Also, to enroll for my online lectures or online test series, email me or message me on Instagram. First of all, remember these formulae. Electrical energy is VIT or I square RT or V square T upon R. Electrical power is V into I, V square upon R or I square R. Depending on the question, we will have to decide which formula to use. Now the first question, an electric bulb of resistance 500 ohm draws current of 0.4 ampere. So the data provided is R and I. You should always note down the data while solving, which helps you to visualize which formula would be applicable here. Part A, power. Now power formula is I square R. That would be applicable because I is given, R is given. So we get the answer as 80 watt. And next, potential difference. There are many formulae. I'm going to use I into R, which gives me 200 volt. Next, the third sum. Mark it as IMP. Calculate the current through a 60 watt lamp rated for 250 volt. If the line voltage falls to 200 volt, how is the power consumed by the lamp affected? So we have two questions here. First, we have to calculate the current. Which formula shall we use? Think about it. Well, we'll use I is equal to P upon V, which will give us 0.24 ampere. Now, in the second part of the question, it's mentioned that the voltage falls. So, will the power consumed also decrease? Yes, it will. But how do we calculate that? Now, note that the current flowing through the circuit will also decrease if the voltage decreases. So, be very careful about using the formula here. Think about what will remain constant in this case. Well, that's resistance. Resistance will remain constant here, assuming that the drop in the current doesn't change the resistance much. So, keeping R as constant, we get V square upon P is equal to V square upon P. This is initially and this is finally. Initially the voltage was 250 and the power was 60. And now the question is that if the voltage is 200, what is the new power consumed? So we cross multiply and get the answer as 38.4 watt. Note in sum number 3, the power dropped to just 38.4 watt. Now in question 5, the electric bulb is rated 220 volt and 100 watt. A. What is its resistance? So V and P are given. So what's the formula for R? It's R is equal to V squared upon P. Substitute the values and get the answer in ohm. And B. What's the current, safe current, which can be passed through it? What is the maximum current which can be passed through it? The formula is P upon V, which gives us 0.45 ampere. So the fuse to be used would have been 0.5 ampere. If they give you a fuse of 0.2 ampere, that would be useless in this case. And a fuse of, let's say, 10 ampere would also be of no use. Now the seventh sum. An electric press is rated 750 watt and 230 volt. Calculate the electrical energy consumed. Now energy is power into time. So that will be 750 watt into 16 hours, which is 12,000 watt hour. You should convert it into kilowatt hour because that is the standard unit for measuring electrical energy consumed in houses. You could have converted further into joule as well, but that is not required. Also, the volt given in the question is of no use. Next, the 10th sum is IMP. So mark it. The current is given and the potential difference is given. We have to find the resistance and the heat energy produced. The resistance is V upon I, so that gives us 75 ohm. And the heat energy, or simply energy, is I square RT. That's the formula we should use because we know I, we know R, and we know T. You could have used other formulae also. Try it out. The more you try out different formulae, the more used to you will get to those. So the answer we get here is 180 joule. Mark the 11th sum as IMP as well. What is the resistance under normal working conditions of an electric lamp rated to 40 volt and 60 watt? Since V and P are given, we can find the resistance it's V square upon P. So that's 960 ohm. And then the question is, if there are two such lamps which are connected in series across the same voltage, then why will their brightness appear less? Now we know that if we connect two bulbs in series, we are effectively increasing the overall resistance. So definitely they will glow less brightly since the voltage is same. But we'll have to solve this and prove it. So first of all, we calculate the current. Initially, it was 0.25 ampere. Now in series, we have two such bulbs. So the total resistance will be 1920 ohm. And the new current flowing through the circuit will be 0.125 ampere. The voltage is same, by the way. The total voltage, that is. So clearly, as the resistance has doubled, the current flowing through the entire circuit, that is through each bulb, becomes half. So since less current is flowing, each lamp appears less bright. If you wish, you can further explain that as the current is halved and the heat energy or the light produced is directly proportional to the square of current, that means the bulb will appear less bright because the heat being produced, the heating effect is just 1/4 of what it was earlier. But it is not necessary for you to explain so much. 13th sum. An electric bulb is rated this. What is the energy consumed and what is the time to consume so much energy at 230 volt? So again, 230 volt simply means the voltage remains the same in this sum. It is not useful for any calculation. It is just some information which is given to say that it is working at the maximum voltage. So the energy is power into time, which comes out to be 250 watt hour. Now in the textbook the answer is in joule, but electrical energy need not be written in the form of joule. We could further write this as 0.25 kilowatt hour as well, which is the standard unit. In the next part, they want the time and the energy. The new energy they said is 1 kilowatt hour, which is 1000 watt hour upon time, upon power, which is 250 watt. So we'll have to convert the energy in watt hour because power is in watt. So the time is 4 hours. Next, the 15th sum, mark it as IMP. A bulb is connected to a battery of potential difference 4 volt. Internal resistance is given and the current is given. Now there is some external resistance also of the bulb which is not mentioned. This 4 volt is the entire potential difference. You can call this the EMF as well. But because of this internal resistance, there would have been a voltage drop. That is why the current is just 0.5 ampere. Now the total energy supplied by the battery in 10 minutes. The total energy will be the total potential difference into the total current into the time, and time should be in seconds so that we get the answer in SI unit. Yes, we got the answer in joule because we took time in seconds and not in hour. You may convert it into a watt hour or kilowatt hour, but it's not necessary. Next, they want the resistance of the bulb. Now, we know that the total resistance will be the total voltage upon total current, which comes up to be 8 ohm. Out of that, the internal resistance was 2.5 ohm. So the external resistance has to be 5.5 ohm. That is the resistance of the bulb. And using that, we can now calculate the energy dissipated in the bulb. I'm using the formula I square RT. Current remains the same through the bulb and through the circuit because everything is in series here. The resistance we will use is that of the bulb, 5.5 only. And the time is 10 minutes. I'm using seconds so that the final answer is in the SI unit of joule. Now in the 16th sum, there are two resistors A and B and they are connected in parallel. And the voltage is 6 volts. First calculate the power. To do that, we should first calculate the total resistance in parallel. So we use the formula 1 upon Rp is 1 upon 4 plus 1 upon 6. Remember to do the reciprocal in the end to get the final resistance as 2.4 ohm, which is clearly smaller compared to the individual resistances. And now we can find the total power supplied by the battery, which will be V square upon R. V value is given and Rp we found. So 15 watt is the total power supplied by the battery. And now they want the power dissipated in each resistor, or the power consumed by each resistor. Always remember that the power and energy formulae are different. In power, we always have upon T to be considered, which may or may not get cancelled in the formula. So there are two resistances, 4 ohm and 6 ohm. The formula of power is V square upon R. The voltage remains the same in parallel connection. That's good. So we can use the value of 6 volt, 6 into 6. Now R1, the first resistance was 4 ohm, so it will consume 9 watt power. And the second resistance was of 6 ohm, so that would consume 6 watt of power. Which is interesting because it is confirmed that the answers are right since their addition gives us the total power of 15 watt. Now the 18th sum. Water in an electric kettle connected to a 220 volt supply takes 5 minutes to reach its boiling point. How long will it take if the supply voltage falls to 200 volt? Definitely now the time taken will be more than 5 minutes because the voltage is less. So what is constant in such a scenario? The amount of heat required to boil a fixed amount of water is always the same. So the amount of energy is constant. So that's the hint to solve this sum. The energy required remains constant. And what is the formula of energy? It's V square T upon R is equal to V square T upon R. Since there is no mention of I in the sum, I have not used that formula. R and R gets cancelled because the resistance of the kettle remains the same. Since nothing is mentioned about the resistance changing, we can always state that it remains the same. So now what is left is the initial V into time and the final V squared into time. And the final time is what was asked. And we got the answer as 6.05 minutes. And we should never leave the answer like this. Because naturally, if you were to tell somebody that it will take 6.05 minutes, it doesn't make sense. And no, it doesn't mean 6 minutes and 5 seconds or something. Because 1 minute has 60 seconds, not 100 seconds. So we convert the decimal part into seconds by multiplying by 60. So it turns out to be 6 minutes and 3 seconds indeed. So we have to solve like this. Next, the 21st sum. By the way, the 18th sum was IMP. I hope you're marking them. The 21st sum, a geyser is rated, the power and voltage is given. Calculate the current drawn. And then the energy and the cost. Current formula is P upon V, which comes up to 6 ampere. Energy is power into time. We get the answer in in watt hour initially. And then we convert to kilowatt hour by dividing by 1000. Because that's the unit being used to calculate the cost. Per unit cost was 4 rupees 20 paise. So the total cost will be rupees 300.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.